All right, we're going to just finish really quickly with the Gaussian elimination so that then you can get some coding practice. So here we have Gaussian elimination. And what we said last time is that when we have a matrix like A11, A12, A13, when we have this A21, A22, A23, and so this was just an example 3x3 matrix that we were using, and the purpose that we were using it for was so that it could help us with trying to understand what the algorithm of Gaussian elimination is from the perspective that we want to be able to make some good code here. And we want it to be general, but sometimes it's hard to figure out the general case just by looking at a problem. So oftentimes it can help by breaking it down into do a simpler one, try to figure out what's the algorithm behind it, and then make it more general. So last time we were just looking at this 3x3 and we said, okay, originally we start with like a system of linear algebraic equations. There's 3 unknowns, 3 equations, and we can set them up in this matrix form. And then what we would like with Gaussian elimination is to be able to get, not there. We want to be able to get all of these entries to go to 0. And then the purpose of that was so that then we could do back substitution. So getting these to go to 0 was the forward elimination. Then we can do back substitution. And just to remind us of what the back substitution looks like was, or I guess, sorry, what sort of like the forward elimination part, I guess. What we were doing was to go step by step. So for the forward elimination, we want to modify some of the entries in our original matrix to the point that what we end up with is after like trying to eliminate, so first we have to eliminate all these entries in the first row because we said we're going to want everything below the diagonal to be 0. So eventually we want to get this one to be 0 too, but they're first we take it by, let's go down the row, and then we'll move over a column and we'll do down the row again. But so in this case, if we go down the first row, then we end up with what we have here, where the first row remained the same, but then because we did what we had last time, which was that we took row 1 times the negative A21 over A11 plus row 2. And this became our way that we got the entries that we have here. And then so because we multiplied a row and added it to the one that was originally here, we have different entries here and here now than we had previously. And then we did a similar thing for row 3, where what we did was we did row 1 times negative A31 over A11 plus row 3. So then that's how we got what's here right now. And then we had x1, x2, x3 is equal to v1, b21, and b31. So that's also important, is to note that the second and third entries of the B matrix or B vector also changed, and the reason for that becomes quite clear if you look back at the fact that these are actually, so A11 x1 plus A12 x2 plus A13 x3 is equal to B1 is an equation. Then the next line makes an equation with B21, so when we had to multiply the row 1 by this number and add it to row 2, that also included these B parts because those are in the same equation as the rest of their row. So then, just to be clear then on what is the algorithm kind of mathematically that we could write out for what we just did, because that's very helpful from the coding perspective, writing out what we just did mathematically. Because all this is great and abstract kind of in the way of, like, it allows us to write at the level of abstraction of saying, like, okay, there is a matrix entry here, and I know it's modified compared to the prior one, for example. But then this, as it's written right now, doesn't give us a really good coding sense because it doesn't show us, like, how is this related to the numbers that were originally there, which is what we're going to operate on in a code. We're going to operate with some set of numbers that is originally there. So to show what happened, so now I'm going to write the term by term what the like row 1 times whatever the A21 over A11, that idea. I'm going to write that now term by term. So then this A221 is equal to A22 minus A21 over A11 times A12. So as you can see, A321 is equal to A32 minus A31 over A11, A12. So that takes care of these two entries for us. That's what they were mathematically. Well, then, due to space limitations, I must erase, despite that I have just written this right here. Hopefully you can see it, and pause for a second if you need to write it longer. So then, the next thing we have is A231 is equal to A23 minus A21 over A11, A13. And then A331 is equal to A33 minus A31 over A11, A13. So there you go. I'll stand here for just a second, give people time to copy. And then if you need extra time, since this is a movie, there's the pause button. It's excellent. Give you infinite copy time. Okay, there we go. Then we have B21 is equal to B2 minus A21 over A11, B1. And then finally, the B31 is equal to B3 minus A31 over A11, B1. You can tell from this was very systematic. This could definitely get coded because what we did, we multiplied one row by functions of the entries in another row times divided by the first number here, and then we added two rows together, and then we got what's here, and then that can very easily be coded in a computer. So then now, the last part that we have to do, we need to get this number here. We want to get this to be 0, but so when I do that though, then we're going to do that through a very similar procedure to what we did in the first row. This time we'll do it slightly differently because we're going to do it with respect to the A221, so we'll multiply whatever was in the third row by the negative of the third row entry right here divided by this number, and then so it's very similar in concept to what we did for the first row when we had number here and we multiply by the negative of this number divided by this number and then add the two rows. So then, but in the end, when you get this here, it's going to have a form like this. So now, as you can see, there's these two here for the B3 and the A332. That's because doing what I just said, which is where we're going to take a term in a row, then we're going to subtract the term that was originally here divided by A221, which is originally here, and then times A31, because we're adding the two rows together. So then the B32 is equal to B31 minus A321 over A221, E21. So then you could see how we could basically loop this for arbitrarily large matrices, because this, if you really sit and you think about it, basically whatever procedure we did on the first row, we just did it again right here, and it was related to whatever's the entry in the row where we're trying to eliminate all the entries below the diagonal. So in the first one, we said, okay, the diagonal entry is A11. So everything below that I'm going to get to be 0. And then the way that we did that is we said, I'm going to take row 1 times the negative of whatever entry is here divided by this entry, and then sum the two rows together. We did that with this row and that row. Then we came here and we said, okay, next one, I'm on the diagonal now, so I want everything below the diagonal. Same thing to go to 0. I'm going to do the same thing. I'm going to take this row, I'm going to multiply it by the negative of the number that was here divided by this term, and then so multiply that whole equation by this, and then I'm going to add the resulting rows together. So I get a 0 here, and then I get a number here. And then why is this great? Oh, so that does lead very, you can go ahead and code, because now you have kind of an algorithm in your mind that's very specific in terms of, like basically in terms of columns and rows. And so you can think of it in terms of maybe a for loop in a coding program. And then here we have back substitution. So now we okay, so now we see why we wanted to get ourselves in this form, because it makes it really easy to code the sense of going backward to get all the values of all your x's. So because of this, we can see that x3 would be b3 2 over a3 3 2. And so that would also not be hard to code in terms of columns and rows. Then two more here. So I'm going to erase this and then put the last two. So then x2 is going to equal b2 1 minus a2 3 1 x3 over a2 2 1. And you can see here that if you were to take the x3 entry and calculate that first, because that one we just could have readily calculated from the formula we just wrote on the board, then now this whole right hand side is in terms of things you know. So now you know x2. And then that's why this is sort of back substitution, is because we're going sort of backwards up the matrix, and by doing it term by term we're able to just get all the numbers explicitly. So here again, you know x2, you know x3 by the time you've calculated this and this, and so you just get this number. And so that's how to do the Gaussian elimination. Important points are related to the fact that this, so I guess one thing, this can have a lower number of arithmetic operations than doing the inverse. So then that was a motivation for saying, like, why would anyone look at this method compared to just like whatever the first thing was that came into their head, is because sometimes some methods do a better job than other ones of just taking less time, and that can be very important, like if you have very large matrices. Then the other takeaway from this was just like trying to see how you can use the small scale example in order to help yourself with thinking through coding, and of pretty much any time you have an algorithm that you want to code, a lot of times it's going to be helpful. And then trying to be able to write generally. So when you write a code, doing it in a general sense. So like if I was to write a code for Gaussian elimination, I would not write it in terms of oh, like every time I have a matrix, I'm going to write one that does this. So like I'm going to explicitly code it in terms of row 2, row 3, etc. You want to code it in terms of general rows and columns, because this procedure is not specific, for example, to a 3x3 matrix like we have here. If I had 4x4, if I have 5x5, if I have any square matrix here where the determinant is non-zero, so there's a solution to the ax equals b type problem, then what I should be able to get here is I should be able to just pull out the solution to any of those. So you want to be able to write codes by looking at ones that are maybe on a smaller scale, but then by seeing the algorithm on that level, then you should be able to generalize it, especially by thinking in terms of things that hold for any matrix. Like what I was saying in terms of like, think in terms of here, how would you code this in terms of rows and columns? Because every matrix is going to have rows and columns, and and those are indexed, but you don't have to necessarily and you can always say like, well, how many rows and columns? And so always like the number of rows and columns can be one of the factors that is guiding your matrix, but you wouldn't want to write it so specific that like, oh, my code only works for 3x3. And then if you want to do the exact same thing with a 4x4, can't use mine anymore, because then, I mean, it's not so general, and you want to do general. So hopefully that shows a lot of things, and so good luck with some coding.